Using Wikipedia graphs to recommend related topics. Okay, so here is our guiding question. So our goal was to make a recommendation tool that takes in two topics and outputs new topics related to both of the inputs. So our motivation for this goal was to create a tool similar to a you might also like tool as you would see in like Netflix or something like that. So our data set was a graph full of Wikipedia articles, which had more than 4 million nodes, with each node being a Wikipedia page. It also had more than 100 million edges, with each edge being a link between the pages. So this graph was an unweighted and a directed graph. So our expected results was that it should mimic basically how a human would think. So if we give it two inputs like Italy and food, it should return something like pasta or pizza, whereas in reality, it actually returns Emilia Romagna, which is a region that's known for its cuisine. Okay, so here's how we approach this problem. So first of all, we need to trim down this data set because 4 million nodes is frankly way too much. And so first what we did is that we use a threshold for the in degree or ingoing links for all the nodes to cut all the vertices that didn't pass the threshold. So this threshold that we used was about 450. So basically 450 ingoing links. And so after this, we have about 24,000 nodes, which is much fewer than what we had before. Then after this, we ran a BFS with three different starting points, the US, animal, and food, which are three general categories or three seed nodes. And then the BFS traveled up to two vertices away, and all the nodes that were not within this distance were cut from the data set. And after this, we have about 15.5 thousand nodes, which is a lot easier to work with. And then from these nodes, we were able to write out an adjacency list in a CSV format so that it could be loaded easily and efficiently.
So yeah, finding a related topic, we wanted to abide by the criteria that the node should be on the shortest path, so that it was somewhere along the connection between the two input topics. It should also be a non-obscure topic so that our results actually mean something. And then it should also be related to both of the input topics. So our process for solving this problem was to use BFS to create a predecessor map that would store all these shortest paths. Then we'd want to pick the middle node on the shortest path between the two topics, so that the output was related to both of these. And if there are multiple shortest paths, we want to pick all of the nodes that are at a middle distance between the two nodes. And then we'd want to pick nodes with an average between this centrality value, which we do by picking the median from the group of nodes in the second step, sorted by centrality. The purpose of picking the median instead of picking very high or very low between the centrality value is that a high value would always return the same nodes that had these high values, like United States or World War II. Something that would be too low would return topics that were irrelevant or just didn't make sense. So yeah, the algorithm that we used was Brandy's or the betweenness centrality algorithm. And as you can see by the provided formula, it was basically a summation after we traversed through the entire graph of sigma of STV, which is the number of shortest paths between nodes S and T that includes V on its path. And in the denominator, we had sigma of ST, which is just the number of shortest paths between nodes S and T. And once this summation was applied for, every single input, we generate this betweenness centrality map. And then the runtime for this algorithm was O of n times m. N is the number of nodes, m is the number of edges. The problem with this was that this took much longer than we anticipated. It took about 6 hours to run on 15.5K nodes and 952K edges. So it was much more costly than we expected, and we had to reduce the size of the data set. However, it was still a very efficient way of calculating the betweenness centrality of every node in the graph. And for our output, we basically got a CSV file in the form of a node index and its betweenness centrality, which was written into a file and saved, and this can be loaded into a map in about over a second.
Okay, so for an alternate approach, we use Kosaraju's algorithm for strongly connected components. Our original motivation was to have a recommendation tool that takes a single input article rather than two. Um, and so it identifies the strongly connected components that contains the input articles, and then outputs the neighboring nodes in the strongly connected component, which are ideally related. So for the development process, first we recorded the original DFS, then created a transpose of the input graph adjacency list, then DFS again on the transpose graph in the order of the original DFS, and then added connected components when visiting each node. And so we didn't really have that many challenges with this algorithm. We just had to adjust the code slightly to use an adjacency map instead of an adjacency list, since the indices were not continuously numbered after trimming them down. So unfortunately, we also had some unexpected results when running Kosaraju's algorithm. Uh, for one, the entire graph was basically one strongly connected components with about three nodes of the 15.5K that weren't uh, included. And even after getting rid of all the one-way edges, the majority of the graph was still a single strongly connected component. And it wasn't possible to return the other strongly connected components because the set of strongly connected components was pretty much the entire trimmed data set. And this kind of just shows how connected every article is on Wikipedia. And if you go on a tangent long enough, you can pretty much get to like any article. Now for the results. First, betweenness centrality. So for betweenness centrality, the output matched our expectations. The top six nodes with the highest betweenness centrality were all extremely broad topics, which makes sense. Some of them were United States, France, United Kingdom, World War II, India, New York City, all very broad articles with lots of connected components. And most vertices had a betweenness centrality between 5,000 and 200,000.
All right, so now for the results of the related topics tool. So when we inputted skiing in Germany, this is one of the better examples. It gave Alps, Norway, and snowboarding. And for clarinet and the composer Leonard Bernstein, it gave saxophone, Mahler, another composer, and Benny Goodman, who's a clarinetist. And for United States and piano, it kind of gave country music, blues, piano stuff related to the U.S., I guess. And for the Celesta, which is similar to the piano in the United States, it gave piano and two American musicians. And sometimes we'd run into the problem where two inputs were directly connected, so then there's no shortest path in between them. And to work around this, we just look at the neighbors of the first topic, and then looked for a node with a similar betweenness centrality as the second topic to kind of give something of similar significance. So for Beethoven and Mozart, it gave violin, syphilis, and alcoholism, which are technically related to all of them, but some of them are a little bit weirder. And then sometimes the algorithm just didn't work very well. Like with dessert in France, it gave Europe, United States, and the Industrial Revolution, which aren't really related to either of the two. Now for some takeaways. So some limitations of the dataset were that first, Wikipedia pages that aren't related are often still linked together, which can make the output seem really random at times, like with the last example. Second, the edges aren't weighted, so there's no way to tell the strength of connections. Like for example, dessert should probably be much more strongly connected to like cake than it is to like the Industrial Revolution. Third, the algorithm couldn't identify themes. Like with Beethoven and Mozart, while technically syphilis and alcoholism are related to both of them, you don't really think of them when you think of Beethoven and Mozart. You would think of something music related, so the program can't identify these themes. And finally, the program was not commutative. So if you switch the order of the inputs, it won't yield the same results, which is kind of counterintuitive.
Some future directions that we could take the project in are applying a stricter definition of edges and weights, potentially a text search option that allows the user to not just have to input the full Wikipedia page title, identifying clusters like World War II, Vietnam, music in the United States, and also adding a randomness component so that if you input two strings, program won't always give the same output because that wouldn't be very conducive or practical. Yeah, so in conclusion, Wikipedia is massive, computing limitations are very real, graphs are very powerful in what they allow us to do. So thank you for listening to our presentation.